So we've talked about one way to solve analytically differential equations. And those were the class of separable equations. Now we'll describe another class of differential equations, first order differential equations, that may be solved, and we call them linear equations. So what is a linear equation? A linear equation is a first order differential equation is said to be linear in the variable y if it has the form that we see here. Okay, so we're only looking at first order differential equations, even though there are higher order differential equations. Here, for this purpose, we'll be using linear for first order differential equations. And specifically, the differential equation has to be linear in y. Okay, and so we could write it in this form here, the differential equation, where these coefficients only depend on x, and on the right hand side you only get an expression with x. So we could put this linear first order differential equation in standard form by dividing by a1 of x, and this here is called standard form, and this is what we'll be working with. So for this section, we will assume that the first order differential equation may be put in standard form, and that p of x and f of x are continuous on I. So in general, linear equations are not separable. Okay, so that's a different class. And notice on the left-hand side here, you have a derivative of y and you have y. And this sort of makes one think about the product rule, right? The product rule, if you have a product of y with another function of x, then the derivative on one function times the other plus the derivative of the other function times the former suggests that we could use the product rule to put this left-hand side in a more convenient way. But in general, this left-hand side is not going to be so we couldn't write this as some derivative of a product of two functions in general, okay? So what could we do? Well, we could try to multiply the left-hand side by some function, okay? This function will be called the integrating factor. And that'll allow us to write this expression on the left-hand side as a derivative of a product, okay? And so why do we want to do that? What's the big picture of all of this? Well, it's very easy to integrate a derivative, right? So if we could write this as a product, then all we'd have to do is just basically integrate the left-hand side, and we'll get rid of that derivative. And whatever we had to multiply this with the left-hand side with in order to get that product, we'll multiply f of x with and integrate that. And then we could set the integral of the left-hand side equal to the integral of the right-hand side. That's the big picture of where we're going. But first, let's try to find this integrating factor, which will allow us to basically write the left-hand side as a product. Not exactly the left-hand side, but the left-hand side times the integrating factor. So here we have a theorem. If we take the integrating factor to be this, then d dx y mu is equal to mu dyx plus mu pxy, okay? So we can't write the left-hand side as a product, a derivative of a product, but we can write this expression as a derivative of a product if we choose mu to be that, Okay, and we go through a proof here. So the left-hand side, we'll take the derivative, and we get this, okay? So that's the left-hand side, pretty straightforward. And the right-hand side, we have this over here, okay? Now we want the left-hand side to equal the right-hand side. So we set them equal to each other, okay? And we could, cancel these two factors, just subtract them out. And we end up with this here, which gives us that either y equals 0, trivial solution, or what we're interested in is this differential equation, okay? Now, how do you solve that differential equation? It's separable. So what you could do to solve this differential equation is separate the variables, and here you have mu, and integrate, and we're going to just do this, in a general way, and you get mu of x is equal to a constant times this, and we're going to just choose that constant to be 1, okay? Without loss of generality, we'll choose it to be 1, because the purpose of mu anyway is just to get some function that when we multiply the left-hand side with it, we end up with a derivative of a product, okay? So let's look at what we bought ourselves, because this is a little confusing, right? I mean, we didn't really solve for the left-hand side in any way, and here we are, we're changing our differential equation. We're actually changing it by multiplying it by mu. But let's follow why we just did that. So when we multiply the differential equation, so if you ignore mu there, this was our original differential equation. We multiply by mu on both sides, okay? So this is still true, okay? And then what we just showed above is, well, the left-hand side of the differential equation is equal to the derivative of the product. And so now let's equate this left-hand side with the right-hand side. And so we have this expression right there. And why we did all that is because it's easy to integrate that term. Okay, so on the left-hand side here, when we integrate, we're going to get just mu y. All right. And when we integrate this, we'll have this, we could take this integral more straightforwardly, right? And we'll get a plus c there. So that's why we didn't bug about leaving a c up here. We're going to have the freedom to solve the initial value problem, but with just this c there. And so notice what just happened, okay? We have this y there, and we have this integral. Well, we could divide by mu. Now, we just move that mu to the left-hand side, and all of a sudden we have an expression for y. Okay? We have an expression for y in terms of x. And what is mu? Mu is what we found up here, which we could write it out fully. So here's a complete, solution to this problem. Okay? We could, instead of e to the integral p dx, we could just put that minus, because 1 over e is equal to e to the minus 1, okay? And that's all that's going on the right-hand side. We do it for this and that. So, but basically this or this is a formula purely in terms of x. And so this kind of seems like magic, right? You start with this differential equation that is not separable, so you don't know how to solve it, and all of a sudden you have a solution. But it's not, okay? And the reason it's not is because the ultimate character of the differential equation, that this relation here still holds true if you multiply the left-hand side by mu and the right-hand side by mu, right? You take an equation, as long as you do something to the left-hand side that you do to the right-hand side, you're fine. Now, you could lose or gain solutions, so you got to be careful. For example, if mu is 0, that might get rid of another solution. Or if mu would somehow have a 1 over 0 term, that might also preclude other solutions. But in general, speaking generally, you know, all we did was just take an equation and multiply it by some factor, okay? And so it remains true. It remains whatever solves this equation, in general, will solve the other one, right? So whatever solves this will solve the other, with the few caveats that I was saying. And so once we're able to express y in terms of x, we got ourselves the solution curves. And this is why this works. Okay, so it's not entirely magic, but it is pretty clever. So now we have this powerful theorem for linear equations, the existence and uniqueness for the initial value problem. Okay. If p of x and f of x are continuous on an interval I that contains the interior point x naught, then for any choice of initial value y naught, there exists a unique solution y of x on I to the initial value problem. Okay, in fact, the solution that we found above, where mu of x is this integrating factor, is the general solution, okay? So that means we found all the solutions. So once we, if we have a linear equation, first order linear equation, then we have the general solution. We could feel rest assured that we found all the solutions. Of course, it's important that p of x and f of x are continuous. Okay? And the proof here, so if we consider the right hand, so if we put this in normal form, if we put this differential equation in normal form, the right hand side we call capital Fxy, then that's continuous. It's continuous because f is continuous and p of x is continuous. So it's continuous in x and y, because remember, we're using the existence and uniqueness theorem that we've discussed before, that a variant of it is called the Picard theorem, Picard-Lindenhof theorem. And, okay, so because these are continuous, this is continuous. And then we have to check one more condition, that partial capital F partial y is continuous, and it is because p of x is continuous. So here I call it the Picard theorem, but again, Picard actually, there's a variant where they use something called Lifshitz continuity. Here we're just looking at partial F partial y. We know that a unique solution exists to the initial value problem. Well then, how can we be sure that that's the general solution? Okay, so we said something stronger. That's all the solutions there of this form. Well, if we found one solution to the IVP, once we put in the initial conditions, we could fix C, right? If we found one solution and it's the only solution, then there can't be any other solution. Okay, so here we have a powerful theorem for linear equations. All right, so let's solve this differential equation. And this is not an IVP, so we're going to find the family. So let's put this differential equation in standard form. So we divide by x, okay, we divide by x the left and right hand side, and we end up with this 4 over x, and x to the 6th divided by x is x to the 5th. Again, you have to be careful with dividing by x. Here x equals 0 is a singular point of a1x. Why? Because a1x is 0 there. That's the point where this is basically what we divided by. We divided by this a1x, and a1x equals 0 at x equals 0. And so we have to be careful there. But anyway, we identify p of x with negative 4 over x, and f of x with x to the fifth e to the x. And here I write we only seek solutions from I is equal to 0 infinity or minus infinity to 0. We're just, without loss of generality, we're going to pursue the 0 to infinity. And why? Why are we stopping at 0? I mean, we're going to, jumping ahead, the solution is going to look like this, and that doesn't have any discontinuities. It's because, again, we divided by that singular point. The point that made a1x be 0, right? So x equals 0, a1x is 0, and so around the singular points we have to be careful. Okay? And all right, let's find mu. Mu, we have an expression for it. We proved above the theorem that this works as an integrating factor, and we just plug and chug. By the way, the e there, exponentiation, could also be written this way. You can see it gets clunky in there if we don't. And so we integrate, we get this. The exponential and natural log cancel, and we get x to the negative 4. And so our left-hand side, after we multiply by mu, becomes the derivative of a product. That was our goal. Okay? And our right-hand side is this mu f of x, which is this once we simplify. Now we're going to, guess what? Integrate both sides. Okay? Once we integrate a derivative, that's easy to cancel, and we just get this. And now we're going to integrate the right hand. This is the integral of the right hand side. That's the left hand side. That's just showing you that you could easily cancel the integral and derivative. We use integration by parts, and doing this like really quickly, you see that you can transfer, e to the x is also the derivative of e to the x. So you could take the derivative from e to the x and transfer it to the other side at the cost of a boundary term. So I do have a video on integration by parts that you could review, and we end up with that expression there. So we have then the left-hand side equals the right-hand side. We multiply by x to the fourth on both sides to get this simplified expression. Okay, and this is only valid for that interval there, because at x equals 0, that's a singular point of this, a1, and so we would get division by 0 in that case. Let's look at another example. So we want to solve this differential equation. Now this is an IVP, right, initial value problem. And our f of x is a little weird, right? It's defined piecewise. So f of x is not continuous in general. Okay, it has a discontinuity at x equals 1, but if we stay away from x equals 1, we are guaranteed the theorem does apply. And it's common to have piecewise defined functions even in science, even though the world is continuous. But you could model, for example, like turning on a switch as a piecewise defined function. So this differential equation is called piecewise linear differential equation because of the piecewise function. And so we break this up into intervals. First we look at 0 to 1, where f of x is equal to 1. And so we'll end up with the differential equation here for this interval there. Mu of x is the exponentiation of the integral of f of x, which is 1 here. And so we get e to the x. And y of x then, if we just apply the formula. So above, when I did this example, I actually walked you through the derivation again, and that's encouraged. But for this next example, I decided to just apply the formula that we have here. Okay? So applying this formula, which this term here is 1 over mu, this is f, this is c over mu, right? Again, just applying this formula right there. Then we could, we get this expression, and we're going to apply the initial conditions, okay? Y of 0 equals 0. That fixes c to -1, so this is the left-hand side is 0, and then on the right-hand side, we plug in 0 into the general expression, so that's what you're seeing there. And so that gives us c1, and plugging c sub 1, which is -1, back into the equation there, the solution that we got, we get this expression at the end for, and this is important, just for 0 to 1. All right, so let's look at the other interval where f is defined, which is for x greater than 0. So we're going to look at this interval here. And now f of x is just 0 there. So notice the contrast between this, the differential equation here for this interval, and the differential equation here for that interval, okay? Now we're looking at this. So that's pretty straightforward to solve. It's separable, and we get this solution there. Now we have a constant, okay? Up here we solve this, we solve for the constant, C1, by imposing the initial conditions. Well, what about C2? Here we could impose continuity. That is, we could glue together the solution that we got up here with the form of the solution here, okay? And so what we do is that, say, at x equals 1, we're going to want y1 at 1 to equal y2 at 1, okay? And y2 is this right here. And so we plug in 1 into the left-hand side, we get this. We plug in 1 into the right-hand side, we get this. And we find that C2 should equal e to the -1. And so now we have this solution that's continuous, okay? And sometimes you'll run into difficulties with differentiability. I didn't quite check that for this, but, you know, I wouldn't be surprised. And that's how you solve piecewise linear differential equations. And I make this remark, okay, that terms that are of the form e to the -x, okay, or like t if we're looking at time, what happens when x goes to infinity? Then e to the x goes to 0, right? And so these are called transient terms, okay? So sometimes you'll get problems where they ask you to identify the transient term. These are terms that go to 0 as x goes to infinity. And why are they called transient? Well, if you get a solution with respect to time, so if you're looking at a dynamical system and you have some solution, say like t plus e to the -t or something, well, as time goes on, that e to the -t term gets exponentially smaller, right? And so it eventually just disappears as t goes to infinity. So it gets smaller and smaller, and so we call this, it just stops impacting the solution. We call it a transient term. Okay, and another example here. Okay, so this equation is not separable, okay? Again, just because you have x plus y there does not mean it's separable. It's not even linear, okay? It's not linear. You could see why because of this y squared term. And in fact, we could kind of rewrite this equation in terms of like dx over dy. So it's not linear in y, but it is linear in x, okay? So if we take the reciprocal of both sides, we get this expression here. So why don't we pretend that the independent variable is y and the dependent variable is x? Okay, that'll give us solution curves to this differential equation, and maybe we could invert the relationship between x and y for some defined interval. And so that's what we do. So we're going to solve for x in terms of y, and here we'll have py, and so be careful, everything that we were doing with x before we're doing with y. And f of y is y squared, so the integrating factor, again, this is 1, because this is minus 1 because that's what py is. It's e to the negative y. We multiply. Now x is the, we're taking derivatives with respect to y, so x is now the function, and so here's our integrating factor multiplied by x. Once we integrate that, you cancel the dy and the integral, and you get this. That's the left-hand side. On the right-hand side, you got the integral mu y times fy, and you integrate that, okay? And you'll use integration by parts here to do this integral. You'll use integration by parts twice, in fact. And you will get this expression there. And here goes your solution. Okay, now this is x in terms of y. And if we had an initial condition, y at x equals 0 equals something, or x equals 2 equals something, or whatever, then we could still impose that, except we have to be careful that we set, so for example, if we had y of 2 equals 3, we'd have to be careful to set 3, we'll set this to 3 and this to 2. So it's just kind of to think backwards, because we took the reciprocal and started solving for x. This can't be inverted for y, but we do have an implicit solution to this differential equation. Okay, this is an implicit solution. So it's a clever little trick. It doesn't fit exactly the definition we said of a linear equation in y above, but it is linear in x, and so let's just pretend then that x is the dependent variable.